Hi, we continue exercise sheet 6 and we'll solve now exercise 3. We have the function f of x that's equal to ln of 1 plus 4x minus x2 minus sine 4x over ex2 minus 1 if x is not equal to 0, because if x is equal to 0, this expression is not defined. And we put the value minus 9 for x equals to 0. So the question is, writing the finite expansion of f in the neighborhood of 0 to a suitable order that we should guess, prove that f is continuous at 0 and calculate f prime of 0. So f is continuous at 0, then f is an extension by continuity of this function, because this expression in here is not defined at 0. So we add a point minus 9 at 0 to define the continuity by the extension by continuity of this this expression in here. Okay, so we need to calculate the finite expansion first to a suitable order to prove that it's continuous. So we need the term of order 0, which will give us the limit of f at 0, and if this limit is equal to minus 9, then the function is continuous. Then we need to calculate f prime at 0. So first we need the term of order 0 that will give us the limit of the function f of x when x tends to x0, and if it's again minus 9, then it's continuous at 0, and the term c1 times x minus 0, which will give us the derivative of f at the point 0. Then in the second question we need to find the tangent to the curve. The tangent to the curve, it means that we need the term of order 0 and the term of order 1 as well. But also we need the relative position of CF and the tangent. To find the position, we need one additional term that is not equal to 0. So whether it's x2 or x3, the first non-zero term after C1. Okay, so let's suppose that this term is x2, so we need to go to the second order at least. Okay, now if we find that this term is equal to 0, we need to push the order one more degree. So at least we have to find the expansion to the second order. Now if we look to the denominator. In the denominator we have ex2 minus 1. Well, ex2, it starts its expansion by 1 plus u, so plus x2, plus u squared, so x2 power 2 over 2, etc. This is the expansion of ex2. Now if we do it minus 1, you will lose the 1 in here. So the first term will be x2. So you have the denominator that starts by x2. That's why if you want the finite expansion to be to the order 2, you have to push it to the order 4 in the numerator and then in the denominator in order to have x2 at the end. So this is the rule. If the denominator starts by an order k and you want an expansion to the order n, then you need to push the expansion of the numerator and the denominator to n plus k. So finally we'll do the expansion to the order 4. Now let's calculate the expansions to the order 4. So we have EU is equal to 1 plus u squared over 2 plus etc. But since u in here is equal to x2, then in this term we'll have an order 4, but in the u3 we'll have an order 6. So we don't need this order. That's why we'll stop at 2 in the formula of EU to finish by an order 4. Then ex2 minus 1 is equal to 1 plus x2 plus x4 over 2 plus x4 epsilon of x minus 1, which will be equal to x2 plus x4 over 2 plus x4 epsilon of x. So this is the finite expansion of ex2, finite expansion to the order 4 in the neighborhood of 0. Now what about ln of 1 plus 4x minus x squared minus sine 4x? We need to calculate the expansion to the order 4. And again, I'm doing to the order 4 to finish with an order 2, hoping that the term of order 2 is not 0, because if it's 0 we need to push the expansion further in order to find the position of the tangent with respect to the graph of f. Now, for ln of 1 plus 4x minus x2, I will consider that the 4x minus x2 in here is u and apply the formula of ln of 1 plus u. I have the right to do this because if x tends to 0, u tends to 0. And for sine x, I will apply the formula of sine u, for u being 4x, of course, because again, when x tends to 0, u tends to 0. Now, if I need the expansion to be to the fourth order, then I need to take the formula ln1 plus u to the fourth order as well, because the u in here starts by x. So even if I go to the term u to the power 4, it will give me some x to the power 4, which will be useful to my terms. So I will go to the order 4 in ln1 plus u and also in sine u. So ln1 plus 4x minus x2 minus sine 4u will be equal to, first, the expansion of ln of 1 plus u, it starts by u, so it's 4x minus x2. So again, this is u, then plus or minus half u squared, so 4x minus x2 to the power 2, plus 1 over 3 u to the power 3, which is 4x minus x2 to the power 3, minus 1 over 4 u to the power 4, which is 4x minus x2 to the power 4, of course, plus x4 epsilon of x. This is for the ln. So again, what you have in here, it's u squared, in here it's u cube, and what's in here, it's u to the power 4. And then for the sine u, you have minus sine u is equal to u, so it's 4x minus u to the power 3 over factorial 3, so it's 4x to the power 3 over 6, plus the term of order 4 is 0 because the coefficient is 0, so it's plus x4 epsilon of x. So this will be equal to 4x minus x2 first, then minus half 16 x2 plus x4 minus 8 x3. So I need all the terms in this term in here, then plus 1 over 3 times 4 to the power 3 x to the power 3 minus 3a2b, so 3 times a2, so it's 4 to the power 2 times x2, or x2 times x2, it will be x4, and then the ab squared will be x times x to the power 4, which is x5, we don't need it, and then the b to the power 3, it will be x6, we don't need it neither. So we stop here for this term. Then from the last term we will have 4 to the power 4 x4 over 4, and that's all what we're gonna take from it. So this is for the logarithm part, minus 4x minus 4 to the power 3 x3 over 6 plus x4 epsilon of x, and here also we can add x4 epsilon of x. So this is equal to 4x minus x2 minus 8 x2 minus x4 over 2 plus 4x3 plus 64 over 3 x3 minus 16 x4 minus 64 x4 minus 4x and plus 64 x3 over 6, which will be equal to minus 9x2 plus 36x3 minus 161 over 2 x4 plus x4 epsilon of x. Of course, here we have always x4 epsilon of x as well. Then f of x will be equal to minus 9x2 plus 36x3 minus 161 over 2 x4 plus x4 epsilon of x divided by x2 plus x4 over 2, which is the expansion of the exponential x2 minus 1. So now, since we are starting by x2 in the numerator and the denominator, we will take x2 as a common factor and simplify it, and we will end up with minus 9 plus 36x minus 161 over 2 x2 plus x2 epsilon of x over 1 plus x2 over 2 plus x2 epsilon of x. So now we will proceed to the Euclidean division according to the increasing exponents of x. So we need to divide minus 9 plus 36x minus 161 over 2 x2 by 1 plus x2 over 2. So we start the division. Minus 9 divided by 1, it's minus 9. So minus 9 times 1, it's minus 9, and then minus 9x2 over 2. And we should subtract to obtain 36x plus 152 over 2 x2. And we divide again 36x by 1, it's plus 36x. It will give us 36x plus 18x2, and then we subtract again to obtain minus 152 over 2, which is 76 minus 76 x2. Sorry, here it's an x3 in here, so it's minus 18 x3. So if we divide again, it's minus 76 x2, and minus 76 x2 times 1, it will give 76 x2, so we will end up by something to the power 3. Divide by 1, it will be something to the power 3, so we don't need any more, so we will stop right here. Therefore, the finite expansion of f will be equal to minus 9 plus 36x minus 76x2 plus x2 epsilon of x. Now, from this expansion, we can say that then limit of f of x as x tends to 0 is equal to minus 9, which is the constant term. So it's equal to f of 0 given in the definition of f. Then f is continuous at 0. And the existence of the finite expansion to the order greater to an order greater than 1 means that the coefficient of the order 1 is the derivative of f, and f prime at 0 is equal to the coefficient of the term of order 1. So this is f prime of 0. So it's equal to plus 36. So this is what they asked in the first question. They needed us to find if f is continuous, which is the case, and to find the derivative at the point 0. Now for the second question, they want us to find the equation of the tangent. So we know that f of x is equal to minus 9 plus 36x. Then, so we have f of x equal minus 9 plus 36x plus or minus 76 x squared plus x squared epsilon of x. This means that the term of order 0 and the term of order 1 will give us the equation of the tangent. So y equals to minus 9 plus 36x is the equation of the tangent to f at the point 0. Moreover, it means that f of x minus the tangent, so minus 9 plus 36x, is equal to minus 76 x squared plus x2 epsilon of x. So if you calculate the limit of both sides, then the limit of f of x minus 9 plus 36x when x tends to 0 is equal to the limit of minus 76x squared plus x2 epsilon of x as x tends to 0. Now if it goes to 0 plus, it will go in here to 0 plus, which is something negative because of the minus 76 in here, so it's equal to 0 minus, it's negative. And if you calculate the limit when x tends to 0 minus of f of x minus 9 plus 36x, it will be equal also to 0 minus, because the 0 is it goes square in here, so it becomes positive, the 0 minus, so it's always 0 minus and negative. Then the curve of f is below the tangent at 0 at the left of 0 and at the right of 0. So if we obtain in here 0 minus and then 0 plus, it means that on one side it's below and on the other side it's above, but here both are negative, so the curve of f is below the tangent at 0. Now in exercise 4 we'll do the same reasoning for this function. So we have ex minus 3 sine x minus 1 in the numerator and ln of 1 plus x in the denominator. So we know that ln of 1 plus x can be written as x minus x2 over 2 plus x3 over 3, etc. Now we want to guess to which order we should go first. Okay, so since in the denominator we start by a term of order 1, sorry, so starting with order 1, then if we want to calculate the expansion, the full expansion to the order n, we need to push the expansion of the numerator and denominator to n plus 1. Now we need to find the tangent, so we need to find the expansion to the order, one order higher than the order 1. So we need one non-zero term after the order 1 term. So let's say we want to calculate the expansion to the order 2. Now again, as I said before, if the order 2, the term of order 2 vanishes, if it goes to 0, then we need to push to the order 3, because we need one non-zero term after the order 1. So first we'll try to do it to the order 2. So to do the expansion to the order 2, then to obtain an expansion or a finite expansion to the order 2 in the neighborhood of 0, we should calculate the finite expansion of the numerator and the denominator to the order 3. So this is why in here we will stop at the order 3 and we'll say that it's plus x3 epsilon of x. Now for the numerator we have ex minus 1 minus 3 sine x. So we say it's equal to 1 plus x plus x2 over 2 plus x3 over factorial 3 plus x3 epsilon x minus 1 minus 3 times x minus x3 over 6 plus x3 epsilon x, which is equal to minus 2x plus we have x2 over 2 plus 2 over 3 x3 plus x3 epsilon of x. Now, to calculate the expansion of the ratio, we'll put f of x as being minus 2x plus x2 over 2 plus 2 over 3 x3 plus x3 epsilon of x divided by x minus x2 over 2 plus x3 over 3 plus x3 epsilon of x, which will be equal to, by simplifying x, to minus 2 plus 1 over 2 x plus 2 over 3 x2 plus x3 epsilon of x over, so 1 minus 1 over 2 x plus 1 over 3 x3 plus x3 epsilon of x. And then we proceed to the division, the Euclidean division. Minus 2 divided by 1, it's minus 2. Then you have minus 2 plus x minus 2 over 3 x2, and we subtract. So we'll have minus 2 plus 2 is equal to 0. Half x minus x, it's minus x over 2, and then we have plus 4 over 3 x squared. So now it's minus x over 2, which will give us minus x over 2 plus x2 over 4 minus x3 over 6, and we subtract. Which will give us 13 over 12 x2 plus x3 over 6, so plus 13 over 12 x2, and then the terms that we will obtain later will be x3 and more, so we don't need them. So this is the expansion, which means that f of x can be written as minus 2 minus x over 2 plus 13 over 12 x squared plus x squared epsilon of x. And now we can conclude the limit of f of x when x tends to 0. So this is the limit of f of x when x tends to 0, so it's equal to minus 2. And what's in here, this is the derivative of f at the point 0, so it's equal to minus half. And then for the second question, since f of x is equal to minus 2 minus x over 2 plus 13 over 12 x2 plus x2 epsilon of x, then we can conclude the equation of the tangent. Of course, since this is equal in here, this is equal to f of 0, then f is continuous at 0. So for the tangent, so I take the term of order 0 and the term of order 1, and I say that y equals to minus 2 minus x over 2 is the equation of the tangent to f at the point 0. Now to investigate the position of the tangent with respect to the function, we remark that the limit of f of x when x tends to 0 plus or 0 minus, it's the same thing because we have x squared in here, minus 2 minus x over 2. In both cases, it's the limit when x tends to 0 plus minus of 13 over 12 x2 plus x2 epsilon of x, which is equal to, since we have x squared, so 0 minus and 0 plus will become 0 plus, so it's equal to 0 plus positive. Then the curve of f is above the tangent at 0 on the right of 0 and on the left of 0. We move now to exercise 5, where we need to calculate the finite expansions to the nth order in the neighborhood of a point x0, which is not equal to 0 in this case, of the given functions. So if we take the first function f of x equals to square root of x, we need to calculate the expansion to the order 3 in the neighborhood of x0 equals to 1. So what we need to do is, whether you can calculate the Taylor expansion to the order 3, so you need to calculate the first derivative, second derivative, third derivative, and then add the point 1, or we can make a change of variables and use the expansions that we already know are at the in the neighborhood of 0. So we let u be equal to x minus 1. So if u is equal to x minus 1, this thing goes to 0 as x tends to 1. So we transform our neighborhood from 1 to 0. Then f of x will be equal to square root of 1 plus u, which is x. And we know the expansion of 1 plus u in the neighborhood of 0, so we calculate the finite expansion in the neighborhood of 0 to the third order, and it's 1 plus half u minus 1 over 8 u squared plus 1 over 16 u3 plus u3 epsilon of u. So all we need to do now is to replace u by x minus 1, so it will be equal 1 plus half x minus 1 plus or minus 1 over 8 x minus 1 squared plus 1 over 16 x minus 1 to the power 3 plus x minus 1 power 3 epsilon of x. So of course epsilon of x minus 1 or epsilon of x is the same thing. It's something that goes to 0 as x tends to 1. So epsilon of x tends to 0 as x tends to 1. So this is the finite expansion in the neighborhood of 1. Now for the second function, we have f of x being equal to ln of sine x, and we need the finite expansion to the second order in the neighborhood of pi over 2. So we do the same thing. We will make a change of variables to go in the neighborhood of 0. So let u be equal to x minus pi over 2. Then f of x will be equal to ln of sine u plus pi over 2. So now it's a function of u. I will call it like g of u. So it's finite expansion. To calculate its finite expansion, I will calculate the finite expansion of what's inside and then for ln. But sine u plus pi over 2 is cosine u. So it's equal to ln of cosine u. Now ln of cosine u, we already calculated the finite expansion of this function in exercise 2. So from exercise 2, this is equal to minus 1 over 2 u squared plus u squared epsilon of u. So it will be equal to minus 1 over 2 x minus pi over 2 to the power 2 plus x minus pi over 2 to the power 2 epsilon of x, where epsilon of x goes to 0 as x tends to pi over 2.